20.2 molar specific heat of an ideal gas. In this session, we will explore the molar specific heat of an ideal gas. We will begin by discussing the internal energy of an ideal gas and how specific heat depends on the thermodynamic path taken during a process. This leads us to define two specific types of molar specific heat, one at constant volume and one at constant pressure. We will also examine the ratio of these molar specific heats, represented by the Greek letter gamma, and see how these concepts apply to monatomic gases. Understanding these topics is essential for describing how gases store and transfer energy during temperature changes. First, let us look at the internal energy of an ideal monatomic gas. For a monatomic gas, the atoms are treated as point masses, so their only form of motion is translation through space. Because there are no rotations or vibrations, the internal energy, E sub int, is equal to the total translational kinetic energy of all the atoms. For a sample containing n moles of gas, this internal energy is calculated as 3/2 times n times the universal gas, constant R times the absolute temperature, T. An important takeaway here is that internal energy is a state variable, meaning its value depends only on the current temperature of the gas, regardless of how it reached that state. To illustrate this, consider a tank with a volume of 0.300 cubic meters containing 2 moles of helium at 20 degrees Celsius. To find the total translational kinetic energy, we first convert the temperature to 293 Kelvin. Using our formula, the internal energy equals 3/2 times 2 moles times the gas constant 8.31 joules per mole Kelvin times 293 Kelvin, resulting in 7.30 times 10 to the power of 3 joules. We can also find the average kinetic energy per molecule using Boltzmann's constant. This value is 3/2 times 1.38 times 10 to the power of negative 23 joules per Kelvin times 293 Kelvin, which equals 6.07 times 10 to the power of negative 21 joules. Now we turn to the concept of specific heat in gases. When a gas undergoes a temperature change, the amount of heat energy Q required depends on the specific path the process takes on a pressure-volume diagram. According to the first law of thermodynamics, heat equals the change in internal energy minus the work done on the gas. Because the work done varies depending on the path taken between two temperatures, the heat required is not unique for a given temperature change. Consequently, the specific heat of a gas is not a single, unique value unless we specify the exact thermodynamic process being used. This diagram shows two isotherms, which are curves representing constant temperatures, T and T plus delta, T's. We can see multiple paths, labeled F, F prime, and F double prime, connecting these two curves. Although the change in internal energy is exactly the same for every path because it only depends on the temperature difference, the work done is represented by the area under each curve. Since these areas are clearly different for each path, the heat transferred must also be different. This visualizes why we must define specific conditions, such as constant volume or constant pressure, to have a meaningful measurement for the specific heat of a gas. Because specific heat depends on the process, we define two standard molar specific heats for an ideal gas. The first is the molar specific heat at constant volume, denoted as C sub V. In this isovolumetric process, the heat transferred equals the number of moles N times C sub V times the change in temperature delta, T. The second is the molar specific heat at constant pressure, denoted as C sub P. In this isobaric process, the heat equals N times C sub P times delta, T. These definitions allow us to characterize how a gas absorbs energy under the two most common physical constraints. Let us compare these two processes. In a constant volume process, shown as the path from I to F, the volume does not change, so no work is done. This means all the heat energy entering the gas goes directly into increasing its internal energy. However, in a constant pressure process, shown as the path from I to F prime, the gas expands as it is heated. As the gas expands, it does work on its surroundings, meaning some of the energy being added as heat is immediately lost as work. To achieve the same temperature increase as the constant volume case, you must add extra heat to compensate for this energy loss to work. Therefore, the molar-specific heat at constant pressure is always greater than the molar-specific heat at constant volume. We can establish a very important general relationship between internal energy and the constant volume-specific heat. For a constant volume process, we know heat equals the change in internal energy. By substituting our heat definition, we find that the change in internal energy equals N times C sub V times the change in temperature delta, T. While we derived this from a constant volume path, it actually applies to every ideal gas process between the same two temperatures, because internal energy is a state variable. In calculus terms, C sub V is defined as 1 over N times the derivative of internal energy with respect to temperature. For a monatomic ideal gas, we can calculate these values theoretically. Starting with internal energy equal to 3/2 nRT, we find that C sub V equals 3/2 R, which is approximately 12.5 joules per mole Kelvin. Using the relationship that C sub P minus C sub V equals the gas constant R, we find that C sub P equals 5/2 R, or about 20.8 joules per mole Kelvin. Finally, we can determine the ratio of molar-specific heats, gamma. For a monatomic gas, gamma equals C sub P divided by C sub V, which simplifies to 5/3, or approximately 1.67. These values provide a benchmark for comparing real gases to the ideal model. Let us look at an example of heating 3 moles of helium from 300 Kelvin to 500 Kelvin, a temperature change of 200 Kelvin. In case A, if we heat the gas at constant volume, the heat required is 3 moles times 12.5 joules per mole Kelvin times 200 Kelvin, which is 7.50 times 10 to the power of 3 joules. In case B, heating at constant pressure requires 3 moles times 20.8 joules per mole Kelvin times 200 Kelvin, totaling 12.5 times 10 to the power of 3 joules. The second value is significantly higher because, at constant pressure, additional energy is required to do the work of moving a piston as the gas expands. In summary, we have learned that the internal energy of an ideal gas is a state variable depending only on temperature. Because gases can follow different paths, their specific heat depends on the process used. However, the relation that the change in internal energy equals N times C sub V times the change in temperature is a general rule for all ideal gas processes. We also found that for any ideal gas, the difference between the two molar-specific heats is the gas constant, R. Specifically for monatomic gases, C sub V is 3/2 R, and the ratio gamma is 1.67. To conclude, consider these review questions. First, why is the molar-specific heat at constant pressure always greater than the molar-specific heat at constant volume for an ideal gas? Think about the energy required for work during expansion. Second, does the relationship where the change in internal energy equals N times C sub V times the change in temperature apply to an isobaric process? Use the concept of state variables to justify your answer. Reflecting on these points will help solidify your understanding of how energy behaves in thermodynamic systems.